Greetings, this is Mr. T. We're going to go ahead and continue with the Chapter 1-2 packet. This is the second video. We just finished with compound conversions, and now we're going to go straight into density. You'll notice that I completely skipped percent factors. You can ignore that concept, and we're going straight to density. So let's go ahead and get into a density of a solid, liquid, or gas first. We're going to go to slide 75 first. On the left-hand side, we have these particles that I'm circling. You can also think of these as atoms, and they make up the gas. In the center, we have a liquid. And the particles are a little bit closer, and then on the very right end, we have a solid. So a gas, liquid, and solid. We then have this box right here, which represents a fixed volume. Now, every substance has a different number of particles or atoms that make it up. So when we're comparing our different phases, solid, liquid, and gas, it's helpful to have the same fixed volume. So that means that they have the same box that's placed on each of the individual substances. So that way we can do an equal comparison. Now, if we look inside the box, you'll notice that the gas particles are a little bit farther away from each other than the liquid particles. And then the solid particles are super close. So this introduces our concept of density. Density is a measure of compactness. Compactness. So as you go from left to right, the more compact you are, the denser you are. So it's all about how compact or close the particles are, which determine density. Please note it has nothing to do with the number of particles. So for example, the gas on the left, maybe I have 3 times the amount of particles present compared to the liquid in the center. Regardless, the liquid is still considered denser than the gas. So it has nothing to do with the number of particles, which is why we like dealing with fixed volumes. So that way the size of the substance, we don't worry about it. Next thing I want to get into is mass. So every single particle contains a mysterious substance called mass. Now, between the particles, there's empty space, and whenever we have empty space, there is no mass. So you should see a trend here. The more particles that we have in the fixed volume box, then the more mass is present. So this takes us to our quantitative, our number definition of density. And density can be thought of as the total mass of a substance divided by the total volume. Ergo, it's density. So again, here's another picture. Mass, we tend to use grams. And then volume is a little bit tricky. So we have 3 types of volume units in density. So for a solid, it's going to be grams over, it's going to be grams over centimeter cubed. For a liquid, it's going to be grams over mil. And then for a gas, it's going to be grams over liter. In short, we use liter because it's a much bigger box, so to speak, since the particles are more spread out. So let's get into a solid. assuming that we have a regular size object. Regular means that it has fixed sides. So the best example of a regular object would be a cube. And then if we were going to take its density, we have to go ahead and place this cube on something called a mass balance, which measures the mass. So for example, maybe it says 2.0 grams. And then for the volume, we have to do centimeter cubed, and that means we got to take out our trusty ruler, and we have to measure the x, y, and z axes. So it's going to be length times width times height, or x, y, z, and then that'll give us some area. And because it's, for example, centimeters for one side, centimeters for another, centimeters for a third, centimeters for each of the length, width, and height, then it's going to be a total of centimeter cubed. And hypothetically, maybe we had something that says our final answer with appropriate sig figs is 8.0 centimeter cubed. So then it would be 2.0 grams divided by 8.0 centimeter cubed. And then this would give us a final density of 0.25 grams per centimeter cubed. Now, the other thing we can do is we can go ahead and assume that the cube is an empty container that we can go ahead and fill up. So this is me filling it up, kind of like filling up a cup full of water. Well, I filled up a cube full of a liquid. And we can automatically assume that if you have 1 centimeter cubed, that's going to be equal to a volume of 1 mil if you filled it up. So for liquids, because they have irregular shapes, they don't have fixed sides because it's a blob. It's a blob. Then we have to go ahead and use a volumetric glassware. So for example, I could use a graduated cylinder, which has increments on the side, indicating how many mils, and then I can use that to measure the volume. So for example, I could fill it up. So here it goes up to 1, here it goes up to 2. Now, I am going to have to go ahead and weigh both the graduated cylinder and the liquid, and then subtract out the weight of the graduated cylinder in order to figure out the weight of the liquid. But just hypothetically, for a liquid, I could have something that says 4.0 grams, and then using the volume, it could be 2.0 mils, and then I have a liquid density of 2.0 grams. Oops, excuse me. Let's try that again. 2.0 grams per mil. Now, it's a compound unit, so you'd have to write it as grams per mil. So that'd be the density of a liquid. Density of a gas is when you have the volume, but it's measured in a larger cube, a liter cube, so to speak. Same thing. Hypothetically, I could go ahead and determine its weight. So maybe it's something like 10.0 grams, and then it's 80 liters. And then I'd have to use my calculator and figure that out. And the answer 0.125 grams per liter. So that's for a gas. Now it is possible to convert from one unit to another, because substances such as water can actually change from a solid to a liquid, so then you'd have to use slightly different units. So let's go ahead and investigate that. If I had 8.0 grams per mil, and this was a liquid, and I wanted to figure out what it is in a solid, then I'd simply have to do a compound conversion that we studied earlier. 1 mil is always equal to 1 centimeter cubed. You don't have to worry about breaking up the centimeters into centimeters times centimeters times centimeters. This one's pretty easy to do. 1 mil, 1 centimeter cubed, and then that would give you 8.0 grams per centimeter cubed. Notice it's the same answer. So let's go from a liquid to a gas. In which case I'd have to use 1,000 mils equals 1 liter. So 1,000 mils goes on top, so it cross cancels. And then that would give us an answer of 8,000 grams per liter, or 8.0 times 10 to the third grams per liter. Now, a couple things. Everything is measured. So for example, if I started off with 2.0 grams divided by 4.0 mils, I have to count for sig figs. So the starting value has 2 sig figs, bottom starting value has 2 sig figs. And so the final answer, the least sig figs, is going to be 2 in this instance. So it'd be 0.50 grams per mil. And then you also have to keep in mind equalities, because liters and mils are the same system. They're both metric. Those are infinite, so your starting value has 2 sig figs. So final answer should have 2 sig figs. The conventional one, technically the first 2 are sig figs, the other 2 are placeholder zeros. Although conventional, you don't have to tell people that. And then 1 mil equals 1 centimeter cubed. This is also considered non-measured. So be sure you know how to calculate density, you know how to convert from solid liquid to gas, and you are comfortable with sig figs. So here's another example where it has nothing to do with the number of particles that make up the substance. It's all about how compact they are. So a styrofoam ball is pretty big compared to a little penny, but the styrofoam ball has all of these air pockets inside, whereas a copper penny is completely solid. Consequently, a copper penny will have a higher density than the styrofoam ball, even though there's more atoms in the styrofoam ball. So it's all about compactness. Water is the great exception. So it's the grand exception. So in short, if I were to have a solid, liquid, and gas, you've already learned that the solid, the particles are really close together, liquid is more spread out, and then gas is really spread out. Well, when it comes to water as a solid, or also known as ice, the particles are actually spread out more. Whereas for liquid water, and we'll say aqueous water, the particles are closer. Gas, however, it's completely spread out, so we're only looking at solid and liquid. So water is the great exception. It's the opposite of all other substances. So if I were to sit there and put my fixed volume here, you can see there's a lot more particles inside my fixed volume, so therefore liquid's denser than water. Now water, its particles actually have a V shape to them. So that's why it's written like this. So make sure you know that concept. This shows us different examples of a solid, liquid, and gas. Make sure you have that memorized. Grams per mil for liquid, grams per centimeter cubed for solid, and grams per liter for gases. Here are some real-world examples. You'll notice that the higher the number, the more dense the substance is. So lead is 11.3 compared to water, which happens to be 1, or actually like 0.999. And you'll notice ice, which is the solid form of water, is less dense than liquid water, which is 1. And a lead is 11 times denser. So you could get a question like this, where you're asked to do a simple calculation that we've just been practicing. Please keep in mind the starting values, they're all measured. So 3 sig figs, rounded to 3 sig figs. Please do me a favor, scratch out the 2. That actually refers to a second step. Now we're going to get into something called density of an irregular object. Now we talked about how measuring water is irregular. Well, now we're going to start looking at solid objects that are irregular. So for example, this is a regular object. Whereas this substance right here, let's say it's melted iron, is an irregular object. It doesn't have fixed sides. So the one on the left, you can take a ruler if you wanted to. The one on the right, you couldn't take a ruler to it. So what we're going to do is we're going to get a glassware, volumetric glassware, that has volume increments on the side telling you how much is present. So for example, 1 mil, 2 mil, 3 mil, 4 mil. We're then going to stick our irregular object inside. And what will happen is, when we stick the object in there, it displaces the water and makes the water rise. So the water level or liquid level is now at a higher level. So before, maybe it was at 4.0 mils. But after sticking the object in there, it's going to be at 9.0 mils. So the volume initial was 4.0 mils. The volume final, that's after you put the object in the glass, volumetric glassware, and the volume raised, was 9 mils. So what is the volume of the object? Well, just do final minus initial, and that gives you the volume of the object, 5.0 mils. As a last step, because it is a solid object, we convert it from mils to centimeter cubed. And because we're using the conversion factor 1 mil is equal to 1 centimeter cubed, it's a 1-to-1 ratio, so there's the volume. Now the only thing we'd have to do with this irregular object is also place it on a mass balance. And then just read the mass on there. So hypothetically, maybe it reads 25.0 grams. So if the mass is 25.0 grams, and the volume of the object is 5.0 centimeter cubed. Then we divide mass divided by volume, and then that would give me a final density of solid density of 5.0 grams per centimeter cubed. So in the next two slides, it shows you an example of this. There is my irregular object. Looks like a rough cylinder. We figure out the mass. We put it on the mass balance on slide A3. And then as far as the volume goes, there's what's called a graduated cylinder. It's got numbers on it letting you know what the initial volume is. So that's my volume initial. After we put it in, the irregular object, there's your volume final. And then you're going to do volume final minus volume initial. And then there's the volume of the object. And then convert it into centimeter cubed. And we can do our final density calculation. So you'll be asked to do this for the end of the week's lab. So here's a question that you could see on a future quiz or exam or something along the line. And then there's the breakdown. And then let's move on. So we talked about quantitative ways, that's numbers of determining density. Now we're going to get into something called qualitative. That's a fancy way of just doing general qualities, no numbers. And we can practice something called the floater sink method. So I'll say FRS, floater sink. So using a beaker of water, we know the density of water is 1. So that's for water. We can automatically assume that if we were to sit there and place an object in there, and it falls to the very bottom, if it sinks, then the density is greater than 1. On the other hand, if it floats, then the density is going to be less than 1. You can also assume that if an object sinks to the bottom, it's going to be obviously denser, it's going to be more compact than water, and then the object that's floating is going to be less compact than water. So this is the science behind how boats work. So here's my water level right here. And then boats have empty spaces in them. And the empty space displaces the water. Consequently, it decreases the overall density of the entire boat, even if it's a giant boat, whatever's in there, because there's empty space in between. Then technically there's a lot less mass per volume, and therefore it floats. All right. So make sure you can answer those questions. Here are some examples here. Slide 88, 89 shows you some examples. And then our last topic is density as a conversion factor. Now, we've learned that we can go from mass to mass. So for example, I can go from the unit grams to kilograms, same system. Or I can change the systems and go from grams to pounds. And on a side note, grams right here refers to the mass that's within particles. And we don't really talk about what mass is. Like, what does it mean to have mass? We just say that it exists and it's inside the particle. And it's actually the mass that's responsible for gravity pulling on it, giving it pressure on Earth. But grams refers to the mass within the particles. Whereas pounds is actually the force of gravity from mass. So it's the pressure that's pushing down due to the mass particles being attracted to Earth. So little things like that. But going back, I digress. But my big comment here was we're in the same type of base unit. We're going from or same type of concept of mass to mass. And if we wanted to, we can also convert from volume to volume. And that's mils, for example, to liters, or milliliters to pints. So the top one's the same system, the bottom one's a different system. Now we're going to do something different. We're going to go from mass to volume, such as grams to mil, or we'll go from volume to mass. So volume is the amount of space. Mass is the amount of mass within particles that exist in that space. And we need to use an existing density as a conversion factor. So for example, if the density is 2.0 grams per mil for substance X, I can go ahead and use density as a conversion factor. Now let me walk you through this. If I ever give you the density, that's a huge hint. We're doing a density as a conversion factor. I'm going to go ahead and use my red pen. I'm going to take that 2.0 grams per mil, and I'm going to write it like this again. We can assume that the bottom number, the denominator, is out of 1. And you need to go ahead and turn it into an equality for use as a conversion factor. So I'm going to pretend that there is a equal sign to the side, and I'm going to walk out the denominator and stick it in the numerator on the opposite side of the equal sign. So it looks like this. Now keep in mind, for density, those are measured units. So if the top number is 2 sig figs, then it's implied that the bottom number is also going to be 2 sig figs. So I had to put in the decimal point in 0 for it to be 2 sig figs. This is the most important step that you need to do first when dealing with these density as a conversion factor problems. Turn that initial conversion factor into a nice equality for doing future conversions. So let's go ahead and give you a starting problem just so you can see this in action. So given a density of 2.0 grams per mil, what is the volume in mils for a starting 4.0 grams. So our starting value is 4.0 grams. I'm just going to write it to the side over here. There's my 4.0 grams. I need to set up my conversion factor skeleton that we practiced earlier in the previous part of the slides. I need to use the equality from my density of conversion factor. What goes on bottom? Grams goes on bottom, and mils goes on top. Why? because the grams cancels out, cross cancels out. So I do 4 times 1 divided by 2.0. Please keep in mind we have to worry about sig figs. Starting value has 2 sig figs. And then the equality, density equality has 2 sig figs. So the final answer is rounded to 2 sig figs. So this is going to give me 2.0 mils. So using density as a conversion factor, I converted from mass to volume. Now I can make this harder and ask you to do an additional conversion. So instead of maybe mils, maybe I could ask you to do liters. And I'll use a different colored pen. I'll use green. So 1,000 mils equals 1 liter. So mils would have to go on bottom because mils has to cross cancel. Liters would go on top. And then doing the same calculation over again, I would end up with 2.0 times 10 to the negative 3 liters as my final answer. Or 0.0020 liters as a conventional answer. So expect to have additional conversions in these density as conversion factor problems. So here's an example. What is the mass in kilograms of 875 mils of octane? Notice they gave you the density. So you have to turn density into a conversion factor first. So in slide 90, that's exactly what we do. So, I'm sorry, we turn density into an equality. There's the equality. Although it should really say 1.00. And yes, it's implied in the actual setup. So the starting value is 875 mils. We put the density as conversion factor front. Please keep in mind though, maybe if we started off with liters, we'd have to do an additional conversion from liters to mils. But in this case, we just start off in mils. And then we go to grams, using the density as a conversion factor. And then from grams, we go to kilograms. And then here's our final answer. Here's another problem. Starting value is 285 grams. We turn the density into an equality. And then we put the unit on the bottom that cross cancels. The other unit goes on top. And then we have to convert it into liters. So that concludes our commentary of the slides, finishing density.